Alright, so the last thing we did was fill in all the different values within the table that shows the different populations, the susceptible, infected, recovered, and dead portions of the population as a function of time. So at every different day, those have a different value. And the natural thing to want to do is to see how those vary over time in a visual way. So having a table of numbers like this has all the information in it, but it's not all that easy to interpret. So between then and now, I highlighted the variables, and with highlighted cells within a spreadsheet, most spreadsheets give you the ability to insert charts or tables or graphs or whatever they call them in the particular version that you've got. And just like in the brick and gravity version simulation that we did earlier, the scatter plot is the way to analyze Y versus X data. In that case, there was only one Y data. In this case, all of the different populations should be treated as Y data. Most spreadsheets like this are fairly intuitive and well designed to the point where if you select one column, that the first column is your X data, and every subsequent column is going to treat as an independent set of Y data. So that's a handsome looking graph. Blow that up so that we can see it well. Give it a nice title. This y-axis doesn't have some things that don't make sense on it. Can't have negative people. So set the minimum y-axis value to be 0. And now this gives us something that we could start to interpret. I'll zoom in so that we have a better look at it. All right, so this shows with the parameter set, assumed, reported, the different values that we've got in there, that an initial susceptible population of about 500,000 drops precipitously before day 20. The number of infected people peaks around day 18 or so, above 400,000, and then attenuates down as people recover. So there's nobody else to get sick by this point. Basically, everybody who's going to get it has got it. And then this is simply the slow recovery rate, first order decay looking kind of thing for people getting better after it. And so the decay rate of the infected population and the increase in the recovered population match each other, but there's a slow accumulation of casualties from this as well that results in what looks like a pretty small number down there, but it's really hard to tell quantitatively what the mortality rate is from this modeled pandemic. If we want to actually include that, I added one more thing up here at the top, the cumulative mortality rate, or the final mortality rate. And so this is computed from the data at day 140. So at day 140, this particular cell, the value that's in here, T146, is actually the very last value down here at the bottom. So if we go down to day 140, and over here on the right, this cell down here is T146. That's the number of deceased individuals on the very last day that's being modeled here. And if that's divided by the number of susceptible individuals, that gives us a mortality rate. I don't know why that moved. Should make it clear that in this particular thing, nearly every single person in the population gets it. And that's clearly not been the case in any of the historical pandemics or the current one. And so we should make it clear that the initial population size that we wrote down before isn't the total population, it's the susceptible population. So it's the number of people that are capable of getting it or that will get it by the end. And that may be something that you want to investigate or do some background work on to figure out what the susceptible population is as a function of the total population. There's enough data out there to look at basically what fraction of people in Wuhan actually got the disease as it ran its course through that population. And because that data also exists, we could actually look up a graph of what the incidence rate was, how many people had reported cases as a function of time as the coronavirus or as COVID-19 made its way through that particular population. It could be that this graph looks very similar to what was observed in that situation. It may be that this differs in some subtle way or in some meaningful way. And if it differs in a meaningful way, we're probably going to need to adjust our model to account for something that we've ignored in the simplistic way that we've put all these populations together. If it looks similar, maybe we've captured all of the relevant components. But because we now have a graphical version, visualization of the results, and we also have a numeric value for what are the critical outcomes, we can start seeing how changing different parameters affects those values. So one thing you might want to consider is what if the transmission rate was actually at the high end of the range that was reported by the Lancet. So if we put in 4 for this, what happens? It turns out that the whole thing goes haywire. And the whole thing goes haywire because all simulations, all models have a range of input parameters that they work for. So this like $num pound means like, you know, to hell with you. You've given me a number that isn't a value. It's not representable. And it's not representable because these are turning into 10 to the 178th. These are turning into negative populations. The whole thing goes nuts. The reason it goes nuts is pretty simple. It's that the infection rate is so high that on day 6, the number of infected individuals, the new infections, exceeds the susceptible population. In fact, by about 32,000 people. And when that happens, there's no error checking in the way that we've written these. So this goes to a negative number. There's no such thing as a negative number of people. And so nothing beyond this point has any physical meaning or interpretability behind it. So a transmission rate of 4 is outside of the range of numbers that can be modeled with this base simulation. In fact, even an infection rate or transmission rate of 1.5 is outside that range. You wouldn't necessarily tell it by looking at the graph here, but you're still getting negative values for susceptible populations over here, which are unphysical. So I don't know what the actual range is, but 1.1 gave us numbers that work. Things less than that, 0.4, gave us things that work. And, well, look what happened. When we made it 0.4, the qualitative shape of this actually changed. So it went from being a high peak over 400,000 individuals sick on day 18 to the peak happening at around 300,000 individuals out at around day 40. Well, that's pretty significantly different. If it changes to 0.3, what happens? This pushes it even further, changes the number of cases, but interestingly, doesn't change the mortality rate terribly much. So at 1.1, it was 3.11% total mortality rate. At 0.5, it's 3.08, even though the shape of this changed. So some things wind up being more sensitive, like the peak number of cases, the day at which the pandemic peaks, at which the infected population reaches its maximum. The mortality rate seems to be a little bit less sensitive to that, but we can start asking other questions like what happens if the virus mutates and it lasts longer in the population. Instead of people getting better in an average of 18 days, they get it better in an average of 22 days. It changes the features of this and actually makes the death rate quite significantly higher. What happens if it mutated and people got better quicker? Well, now the death rate went down by a lot. And so you can start seeing the effect of changing some of the assumptions that we built into this. I'll return these to the initial values and ask one other question. What happens if we change the number of hospital beds. So one thing that has been proposed as a possible solution to this is what happens if we just set up a bunch of field hospitals and offer treatment to anybody who comes in the best way that we can. And so if we doubled the number of beds, of ICU units, of ICU care units from 5,000 to 10,000, the shape of this graph doesn't actually change, but the 140-day mortality rate actually went down by quite a bit. So even though it doesn't look like the number of cases changes much, being able to take better care of a larger number of people actually drops the mortality rate, at least with this set of assumptions. You could certainly explain that if you think hard about what the different mortality rates that we've assumed are for people who are receiving ICU treatment and people who are not. So I'm going to suggest that all of these parameters are fair game for changing because none of them are actually known. There's no strictly well-studied, controlled experiment that tells us exactly what any of these values are. So the only way to gain any insight is to see what sort of effect the uncertainty in those values has on our ability to quantify the effects of this pandemic. There'll be a posted sheet with some questions that you can answer using the kinds of methods that I just walked through in this last bit, just playing around. What happens if we change that number? What would it take to do this? So I'll wrap this up and give you an opportunity to start playing with this model. And then later this week, we'll talk about how you will introduce a new variable that would allow you to address a novel question that you wouldn't be able to get at with just the simplistic sort of base case that we created here.